current carrying wire. This can be any direction, okay? So those are the other things you have to get familiar. So if I put the current wire here and the current going upward direction, and we talk about right hand rule number 2. So in right hand rule number 2, thumb direction is upward direction, whereas the current is, okay? That should be the thumb direction. And then you take a look how the other four fingers create the loop around the wire. If you take a look the right hand side, other four fingers going into the plane. So the magnetic field going into the plane thisward direction. And then other side, the magnetic field comes out the plane. So the magnetic field lines is actually create a loop look like this, okay? So the magnetic field loop is actually on X and Z plane relative to the current wire is on Y axis, okay? This loop right here is on XZ plane. That's simple, okay? So if my point of interest, let's say this is our point of interest, if that point is R distance away from the current wire, then we develop an equation by starting from the Biot-Savart law, right? So the Biot-Savart is actually talking about if I have any random wire, if you pick a very small piece of wire length and then go R distance away from the wire, then magnetic field produced due to a small wire piece is going to be mu 0 I divided by 4 pi R square, and then this is going to be dl cross unit vector R, okay? And you can expand this one very easily if you want to mu 0 I divide by 4 pi R square times dl sine theta, theta angle between the delta L and the unit vector R direction. And then we can put here unit vector n, that is the direction of the magnetic field, okay? So that direction you can find easily by using right hand rule. So that's the one you have to practice, because sometimes putting IJK vector is going to be very difficult, because most of the time you're not going to get wire pieces or the direction align with the IJK directions, okay? Because of that, you have to practice how to do this kind of problem conceptually by combining the right hand rules, not just by using the math formulas, okay? And then we use this concept and then build an equation for infinitely long wire, okay? If this wire goes to positive infinity to negative infinity, which means technically the wire can't be infinitely long. Technically, our assumption is that the wire length is much larger compared to the radial distance r, where the point of interest is, okay? Technically, the wire length, let's say like 20 centimeters, then this R can be like maybe 2 centimeters, something like that. Should be very close to the wire that R, okay? So when the R is increasing, the magnetic field decrease by large very quickly. So if I do that assumption and then build an equation, then the last time we talk about that mu 0 I divide by 2 pi R, right? So that's the formula, and then unit vector in the units of the magnetic field is T. So that's the equation we end up. So that's the one we actually testing today, okay? First part, there's two part of the lab. So the first part, we will take a look how this formula is actually working, technically validating that formula. If we can validate by measuring the magnetic field around the current wire, then we can validate the Biot-Savart law, right? So this law is also can be validated. That's the plan. And to do that, what we do, we can measure the current directly. We can measure radial distance directly, right? This is a constant. And the magnetic field also we can measure directly by using the magnetic field sensor. So if I can measure all of these three variables, maybe I can estimate this guy. So mu 0, because mu 0 is actually a constant, right? So that we call the permeability constant. So that should be about 4 pi times 10 to the negative 7. Now, we can estimate that constant experimentally and then take a look whether we getting the number close to the estimated value or not. If we get in the right number or close by within very low percentage error, so that way we can confirm all our formulas and then concept and theories are valid. Okay, that's the plan. Any question? Okay, so then let's continue now. To do that, what we need is we need the wire, which means if we try to do this in-person setting, I need to have a circuit actually, right? So we can't just have a wire. So we have to have the wire is actually connected to the external circuit. That part is not showing up your simulator today, okay? So I have to have a battery, positive, negative, and then we have to have a switch, and then those things are very general. This is positive, negative, so the current will pass through upward direction. And then we can actually, there's various way to measure. We can use a compass like the needle compass, and then needle deflection. We can estimate the value of magnetic field depending on how much needle deflection happens. And then relative to that, we can actually make a table, okay, by changing the current here. Or nowadays we can actually have a magnetic sensor, and then by bringing the magnetic sensor within different radial separation from the wire, then we can detect what's the magnetic field strength around this wire piece. Okay, so I can do this experiment in two different ways. Mainly, I can measure magnetic field strength as a function of current. So then, according to our equation, magnetic field should be directly proportional to the current, right? So then if I put this guy into y-axis, current into x-axis, you can make a graph. So the graph should be linear, right? So it should be linear, look like that. Slope of the graph should be mu 0 divided by 4 pi. So this should be current, this should be magnetic field. And then from there, I can actually estimate the mu 0. That should be just simply slope of the graph multiplied by 4 pi, right? So that's one way. Another way I can, for when you do that one, R must be constant, okay? So the radial distance must be constant. And then we can do the same measurement again by keeping the current constant, but we change the radial distance, then we should be inversely proportional to R. If you do a graph for this one, R versus magnetic field, this should be like exponential decay graph. We can do the power law fitting and then figure out the constant, or we can do actually graph look like this, 1 over R into x-axis and the B, then this graph should be linear. Then by using the slope of the graph again, we can actually figure out what is the mu constant again, okay? So for this graph, slope should be again mu 0 divided by 4 pi. Then the mu 0 gonna be again slope times the 4 pi, okay? But make sure the x-axis for this particular case must be 1 over R. Because we usually like to have the linear graphs. That's very easy to understand the calculation part. Otherwise, actually, we can do the power law fit for this one. So if I do the power law fit, this should be R to the power negative 1. So then by using that one, we can estimate the constant again if we wanted to, but the linear graph is easier. So that's what we're trying to do. It's a very simple experiment because simulator actually will give you very good numbers result. So we will get a good very low percentage error. Okay, any question? All right, so this kind of experiment actually very challenging to do in person setting because the magnetic field around this wire piece, because we can't have this current really large values, but simulator we can apply any, right? So we can even go to like 20 amps. But if I doing like 20 amps for the current, this is extremely large current. So the small wires can easily burn out, and then it's dangerous if somebody have a 20 amps going through the body. That can be a very dangerous situation. So because of that, we can't really do this kind of experiment this way in class setting, because particularly we have to apply current very low values, maybe less than 3 amps. That's the safe range. and the magnetic field around here going to be very, very small, maybe like 10 to the close to 10 to the little above the Earth magnetic field. Earth magnetic field is 10 to the negative 5 times 10 to the negative 5 Tesla, a very small number. So if it is very close to that number, very difficult to separate out Earth field and the real magnetic field coming from the wire. It's very difficult to detect. So, and the separation, you have to bring the sensor very close to the wire. When you measure in the separation, that also create huge error. So nowadays there are the ready-made setup from the Pasco. So those are the good ones to use, but those setups again acting very similar to the simulators because nothing much we can do. The setup is there. We just take in the data by using the computer interface. That's it. It almost very similar to the using a simulator. But it's still, if you're doing that in person, you can see the setup, you can get some physical idea how the setup look like, and then so on. All right, any question? Okay, then let's continue. So the simulator, we're going to using two different simulators. The case A, there's a link on page number 2. First link, okay. It says olabs.edu.in. So just click on that link. Okay, then it should open up this simulator page. If you take a look, it has a wire. You can click on the wire and then change three-dimensionally, see how it look like. Okay. Now that's the wire. Now current is carrying upward direction. If I put the wire into y-axis, look like that. And you can put the wire into different direction if you want. Okay. Now it look like wire in the c-axis. Okay. But I think it not allow us to rotate into x direction. Okay. You can rotate on YZ plane the wire a little bit, but it doesn't allow you to rotate other direction. Okay, the purple icon is the sensor, okay, this guy. So now you can see wire has a current upward direction. If you do the right hand rule, put the thumb into this red color arrow, then your fingers is actually, other four fingers create this circle around the wire. That's the magnetic field lines, okay? Magnetic field line always, technically magnetic field line doesn't have a starting point or ending point, but we can basically say magnetic field lines like we can correlate the magnetic field line similar to the electric field lines. Usually electric field line start from positive side and then goes to the negative side, right? Because by definition, how we define the electric field line, if you have a positive charge particle, that positive charge particle attracted towards the negative, right? So that definition we can actually apply here too. If I have a north pole must attract to the south pole. So we can say magnetic field line start from the north and then ending at the south. That's true. But technically magnetic field lines, that kind of definition has no any meaning because magnetic, even the inside the magnet, there's a field line because the magnetism originally developed because of the electron motion around the nucleus. So if you want to really understand how the magnetism, there are ferromagnetism, antiferromagnetism, ferrimagnetism, canted ferrimagnetism, and then there's various type of frustrated magnetism. There's various type of magnetism we take a look in material perspective. So that's where the material science play a very major role. So what we really interested is generally in terms of application point of view, how to fine tune the magnetism. Then you need actually a lot of variables if you want to fine tune something. Okay. Now in this kind of application, we don't care how the magnetism develop or anything. What we interested is where the magnetic field lines and then whether it is rotating uh, clockwise direction or counterclockwise direction relative to the current wire. Okay, so that's all what we're interested in. If you look at it from the wire perspective, from the top view, now right here you can see it rotating counterclockwise around the wire. And then if I flip the current direction, You can change the current direction by just clicking here. If you click on this small box, current will flip. As soon as the current flip, you can see the magnetic field line direction is actually changes. Okay. So now it is moving clockwise direction relative to the current wire. Okay. If you look at it from the top view. So that's the idea. It's a very simple simulator. Nothing much to do technically uh, in terms of doing the experiment. So this will give you the numbers. We're going to use the numbers to estimate the mu zero. Okay. And the field strength I can measure by changing the position of this purple icon. So that's a radial distance, okay? We go, wire is on y-axis, we go x direction, for example, radially. And that direction you can change by doing here. It's in meters, okay? That's a problem with this simulator. These numbers, there's no way we can detect. If you're doing this in-person class and even no meaning detecting, you can see how small the numbers are. Magnetic field is about 10 to the negative 8 Tesla. That is 10 to the negative 3 lower than the Earth magnetic field. If we try to do that in-person real experiment setting, there's no meaning because Earth magnetic field is everywhere. So you can't really identify what is the Earth magnetic field component, what is the real magnetic field component, that location. So since it is a simulator, I don't know why they put such a small values. They could do smaller numbers on the radius, like maybe a couple of centimeters, then this number can actually automatically increase by about like 2 orders of magnitude. Due to some reason, they use in the distance in meters. That really crazy idea. There's no meaning at all. But that's what it is. That's okay. So as far as we have numbers, we can estimate the mu zero. Okay. Generally, if we're doing this in-person class, this R value should be like we starting like maybe a couple of millimeters, maybe half a centimeter minimum, and then go like every 5 millimeters at a time. Maybe after like 10 centimeters, almost negligible because Earth magnetic field take over. Okay, any question? All right, and also we can change the current. You can see I can change the current. I can just click and drag these sliders right here, or you can just type the number here, whatever the number you like. You can go from lowest, I think maybe 1 amps, and then change the current all the way to like 20 amps. That's really, really large current, okay? Uh, there's no way we can get 20 amps in general settings in our labs. If we have 20 amps, that's a very dangerous situation too. It can burn out or it can kill somebody. Okay. So that's about it. Then we'll start our calculation. Any question? Okay, so let's start with the current direction upward first. Okay. And current number technically doesn't matter. We'll put it that in a reasonable value, maybe like 5 amps, maybe a good number, because anything larger than that is not really practically possible. And the radial distance for the first one will go maybe closest as possible. Closest you can go about like 5 meters. That's really, really crazy. I don't know. This is a simulator. It just they're doing the calculation internally in their program. So they could do any numbers. Instead, they select go from 5 meters and upward. Has no any meaning at all. If they go like this 5 into point 0.5, not the point 0.5, like 5 millimeters, then this number 10 to the negative 7 automatically increase by 3 orders of magnitude. So our Tesla value going to be on the order of 10 to the negative 4. That's practically measurable number. Okay. So due to some reason, either the person who creating the computer scientist has no idea about physics. Uh, I don't want to use the other term. So the otherwise actually a physicist who has no idea about the real physics. Okay. So two things can happen. Okay. Yeah, some computer guy. Anyway, that's okay. So with with our situation, we should give them the credit anyway, right? Because they set it up all of those things last year. Before last year, these are not exist up to this level. Their website is very crappy, difficult to use. But last year, very first few months, when we started in March last year, converting everything into the virtual, they actually did very fast pace. It's from India. They have like billions of people, right? They put it probably hundred of different computer graphic guys, and then build the site up to a really, really good level. So still, we should give them the credit. Okay. Any question? All right, then let's continue. Mainly, we can't do much with this simulator, particularly we just extracting the data and then do the calculation. Okay. So first we'll take a look how the magnetic field value changes, or particularly the magnetic field direction changes with respect to the current, the radial distance, and particularly with respect to current direction. And then after that, in table 2, we'll try to estimate the mu zero, that is the permeability in free space or the air, and then we'll compare that with the existing or the known value, that is 4 pi times 10 to the negative 7. Then for that table, I will put you into a group, okay? And again, this will be optional, either this lab or I think one lab you're supposed to submit, I think this week. You can decide which one not to do, okay? So this one, I think lab report number 6 must be due this week. One of them could be optional, okay? So the report number 6 going to be individual, this is going to be group. You can decide which one to drop. Yeah, but you can decide which one to drop, okay? Because 2 lab reports due, so the out of those 2, you have freedom to decide to drop any one of them. Okay, guys, so let's start from here. Let's start lowest radial distance, possibly about like 5 amps of current. And the magnetic field sensor telling us magnetic field value is about 2 times 10 to the negative 7 Tesla. And the current is on upward direction. Okay, current direction. Let's consider this is Y direction. Okay, we would like to go always relative to XYZ coordinate system, right? Experiment number 6 due this week. It's usually due in 2 weeks, right? So you had last week is the break. I can extend that 1 week if needed. That's totally fine since the last week is the spring break. So we can put it into next week. That can be done. Okay, so the current direction, let's consider positive Y direction. Oops, why is that? I need to, if it doesn't take you, when you put the positive sign in front, I think it will read as a number. That's why you may have to change these 2 cells into home setting numbers and then change into name. Let's see which one gonna work. Text. Okay, yeah, changing to text. Okay. So just highlight these 2 cells, B number 8 and 9, and click on the number, home menu bar, and then click the down arrow, very end, you will see the text, okay? So then it will identify as a text value. Otherwise, it will try to read as a number if you put positive sign in front. So the current value we are using about 5 amps, right? And the unit should be amps. Other problem is that we can't really have many decimal places. That's a disadvantage. We'll add 1 decimal place purposely because it seems to be very, very inaccurate readings. So all of these will add at least 1 decimal place, okay, for these two, which means numbers, and then we'll reduce the decimal place to 1. And the radial distance about 5 meters again, unit meters. That also will purposely add one decimal place, because generally these values can go to all the way to 50. That means two significant figures are possible anyway to measure, right? At least. So we'll keep the two significant figures for all the measurements. So this also will add purposely two decimal places. Okay. And magnetic field value, unit Tesla. And 2 times 10 to the negative 7, that also will write purposely by putting 2.0, okay? 2.0 times 10 to the power minus 7. Okay, so the field direction, this is just an observation, there's no calculation here. Field direction, there's no any units associated with, okay? No units are needed there. And the field direction relative to the y-axis, if you look at it from the top, this is counterclockwise, okay? So we can just say counterclockwise there. Okay, that's about it. Very simple observation. Let's change the current direction and then do the same observation by clicking the icon on the simulator, left-hand side, very top. Current now in negative y direction. And the values are same. We can change the values if needed, but we don't need. We're just observing how the magnetic field change technically, the direction. That's what really we're interested at this point. And the magnetic field, now you can see clearly opposite direction relative to the previous. So that should be then clockwise. Okay. Okay, that's our observation. Okay, table number 1. So table number 2 will do the calculation. Then I will put you back into the put you into the breakout rooms there. And talk to your group members before the class end. Make sure if you want or planning on writing the lab report for this one, if your group members doesn't, you still can do individually. Okay, so make sure you ask them what their plan is. And also if you don't participate, then make sure anybody doesn't participate to the group lab report, don't include their name. Okay, they must get 0. If somebody doesn't participate, that person must get 0, okay? All right, so let's continue then. We will take a screenshot of this one too. Maybe let's take a screenshot in that angle. Yeah, that angle should be better because current value, current direction and everything should be visible, right? So let's place it somewhere here. If you're planning on doing the lab report, that should go into the procedure section. Insert illustration screenshot. Let's take a screenshot of this guy. Maybe this area should be good enough. That should go to procedure section, okay? All right, this should be then figure number 1. Figure number 1, we can say magnetic field due to current wire simulator. Okay, you can name any way you like, just the name has to have idea of what we're trying to do in this experiment. Okay. All right, then let's continue on table number B. Any question? Current, unit amps, magnetic field, unit Tesla, and the permeability unit we have to figure out. So there's a couple of different ways you can figure out the permeability unit. You can take a look at the formula which we're using today. So that's one way to figure out the permeability units. So the formula we are using today is actually B is equal mu 0. There's two formulas we are using today. Mu 0 I divide by 2 pi r. I can actually use this formula to figure out the permeability unit, okay? So if I get the mu 0 out, this is going to be B divided by I times 2 pi r. 2 pi doesn't have unit. B has a unit of Tesla, R has a unit of meters, and then I has a unit of amps. So we can say Tesla meter over amp. And if you want to reduce this unit a little bit more, we can take a look what is the unit of Tesla itself. Because if you remember Tesla unit we define in chapter number 11 when we're doing the magnetic force. Magnetic force is Q times the V cross B. That's where we first define the magnetic field unit Tesla, okay? So this is B is equal F over QV in terms of magnitude only. Then the unit of B gonna be Newton divided by Coulomb, and then V is velocity meter per second, okay? Then meter per second, meter per second, this we can reduce a little bit more. Coulomb per second is amps and then meters. So I can combine these two units if I want to, and then we can reduce units a little bit because Tesla unit, having this unit is fine, okay, nothing to worry because this is a unit which has some of the standard unit we would like to use for different measurement. Tesla is magnetic field, that's fine. Amperes is current unit, that's also fine. Meter is unit length, that also fine. But if I want to look at it this unit different angle, then I can plug it back into the Tesla. Tesla is Newton divided by AM. Then I have meter here, then I have ampere in the below. Meter cancels out. Technically, I can write this unit Newton per amp squared. Okay, so the both are technically the same unit, doesn't matter, okay? We'll use the unit we're getting from this formula. That's okay, because that is a formula we based on. So Tesla meter over amps. Okay, any question?
For figure 1, what was the description you gave it?
I just wrote magnetic field due to current wire simulator.
All right, thank you.
Yeah, just you can type any way you like, doesn't matter. Magnetic field direction, there's no units. Okay. All right, then we'll do the percentage error. Okay, there's no particular unit for percentage error either. We can put the percentage sign if we want to. We'll compare that with the known value. Okay, since the first one we're doing the radial distance fix, we'll fix the radial distance here at 5 meters. Okay. So the radial distance going to be then 5.0 meters. We're going to add at least one decimal place purposely. And then increase the current, maybe how many data points we need? We need about like 8 data points. We can go from maybe 0, 1 amps all the way to like 20 amps. We'll go like from 2 amps, each 2 by 2. Okay. So we'll start from 2 amps, magnetic field. Make sure you add one decimal place purposely, one significant figure. Numbers, one significant figure. Magnetic field about 8 times 10 to the negative 8. That's a very small number. 8.0 times 10 to the power minus 8. And if you, when you're doing the numbers, if you put the equal sign in front, that number will automatically go into like a decimal value, which may not be a good idea to do that way because this is a very small number. Because of that, highlight this whole column, column C, and then change that number into a scientific format. Then the Excel do the scientific format E plus or minus the value, right? So that will write the way Excel like to see that number, okay? Otherwise, by keeping 10 to the power negative 8, the way we generally write is also fine. Excel can read that also. And let's estimate the permeability from this one. You know now the permeability from that should be equal to the magnetic field times 2 pi r divided by the current, right? So let's test it out, that one. Equal sign magnetic field value on C15 times 2 times pi is pi open and close brackets. That will read all the decimal places on the pi. And then multiply by the R is a constant, 5 meters, divide by the current is actually cell B15. Then hit enter. So I'm getting about 1.26 times 10 to the negative 6. So this is the formula or the function I'm using for mu, okay, ability. And let's compare this now. This number, the expected number is 4 pi times 10 to the negative 7. Let's test it out that value first. What is that number? Expected mu, or let's say mu known. Mu known should be equal sign 4 times pi open and close brackets times 10 to the power minus 7. So that's about 1.2566 times 10 to the negative 6, okay? So generally we write 4 pi. When you write in the mu zero, the reason is that most of the time this formula has a pi. Because of that, when we do the analysis part by hand, that pi cancels out. That's why we write mu zero that way. But in the experiment, we would like to have the decimal value, okay? Now let's compare. It's almost the same up to second decimal place. There's no difference at all. Let's compare those two. I'm going to keep this number right here and then equal sign ABS, open brackets, expected value 1 point, let's say 2566 multiplied by 10 to the power minus 6 minus calculated value on D number 15, right? And then divide by expected value 1.2566 times 10 to the power minus 6 multiplied by 100. Very, very small. The reason why it is very, very small, because both numbers are almost the same, okay? Yeah, so make sure you put a parenthesis for this guy, otherwise I think this 100 can multiply with 10 to the negative 6, okay? All right, it's very small, about like 0.00295. Percentage error value should not leave it like this way in scientific notation. Recent percentage error values, we would like to see whether that number is larger or small. This way in scientific notation has no any meaning for that, okay? So make sure you change that into a normal number mode with about like 3 decimal places probably. Yeah, 3 decimal places is enough for 3 or 4. Keep 3 or 4 because otherwise number is not visible. Otherwise, usually we would like to have only 1 or 2 decimal places in generally. But since this number is very small, just you can keep it 4. So that means our calculation is very accurate. So all the measurement we does very accurate. So that's the problem with the simulators, because simulator does the calculation internally. So our percentage error value is going to be very, very small. Okay, any question? Now,
Do you mind putting down just the equations that are highlighted, please?
percentage error
Yeah,
equation.
just percentage error.
Let's do it here.
Thank you.
Yeah. Mu known value, you can mu known value, if you use 1.26, then you will get the percentage error 0. Okay, that's why I purposely keep that extra decimal places, because it's a calculated value. Technically, right? I just multiply 4 pi by 10 to the negative 6. I keep that 2 numbers extra. All right, so you can do the rest. How you have to do this now, make sure we keep in the radial distance fixed, okay, that we're not going to change 5 meters. What we're changing is the current, okay. At a time, you can change the current maybe like 2 amps at a time. Just change the current into 4 and then repeat the measurement, okay, and then 6 and then 8 and then so on. And you can complete that on group setting. I will put you into a breakout session. That will be your group. Make sure you discuss with your group members of the plan, okay? If you're not planning on writing this or last one, discuss with them and then arrange accordingly, okay? Yeah, we'll increase the current at a time by 2 amps, okay? Yeah. Technically, it doesn't matter how much you increase, but maybe 2 amps is good enough. Let's switch on that one too. Okay, any question?
Could you show how you changed the format of the trend line?
Oh, just click on the equation, just one click. Then this window will open up on your right-hand side corner. It says format trend line. And then you will see the category, then change that into scientific. Then it will appear at least 2 more decimal places. We can increase even that by changing this number, okay? You can put 3 or 4 there, then the 4 decimal places appear. Okay, and also we would like to have a graph title, right? So generally if we have a graph, let's name it. This is going to be magnetic field versus current. And the x-axis is going to be the current. current in unit amps, and the y-axis is the magnetic field, unit Tesla. Unit Tesla. Okay, and then what we like to do is that by using the slope, we would like to recalculate the permeability constant, right? So that's what we're going to do on table number 3, okay? Error analysis for the permeability. Permeability units we already done earlier by using our formula Tesla meter over amps, or we can reconvert that into Newton divided by amp square, doesn't matter. Both units are actually the same. So we can keep the same unit here we done earlier. And the average value from the table number 1 gonna be the same, but we'll do that function, okay? Equal average command, average function. Average of this technically no meaning doing it because there's no change at all. Our numbers from the simulator is too accurate, so we will get the same number again, okay? That's the average from the table 1. Let's keep that function somewhere here. Mu AVG. And then do the percentage error, going to be about the same number, but we'll calculate anyway. Okay, equal sign, ABS, open brackets, non-value 1.2566, 10 to the negative 6, 10 to the power minus 6, minus average value is on cell number C46, divide by parentheses 1.2566 multiplied by 10 to the minus 6 multiplied by 100, close bracket multiplied by 100, okay? About the same number like we got earlier table, PE. Make sure PE should show up on the decimal values, not the scientific, okay? Decimal values has, the scientific values has no any meaning when we do the PE or PD. It's about the same number, but I did the calculation anyway because I have to use the function. Okay, so question. Okay, then let's take a look from the graph. From the graph, we know the slope must be equal mu0 divided by 4 pi. And if I know the slope, multiply by 4 pi should be the mu0, right? So let's take a look there. Equal sign, slope is 4 times 10 to the negative 8, equal sign, slope is 4.0 times 10 to the power minus 8. We'll do a parenthesis for this one. I think it doesn't matter, but we'll put a parenthesis for this one. Or we can do the 2 pi from the beginning. 2 times pi open close brackets multiplied by 4 times 10 to the negative 8. Oh, I did 2 pi, that's why. Number is very different. Let's see what happened. B versus I. Oh, it's 2 pi, right? Oh, that's why. Let's take a look at. Yeah, so we're working on this formula. So mu0 divided by actually 2 pi r, that whole thing should be this guy. Okay, so this is the mistake. This should be then mu0 divided by 2 pi r. So I have to multiply this by 2 pi r, that whole constant. Okay, all right. So let's correct it out that one. This should be 2 times pi times r. R is 5 meters, right? That's what we kept constant. Okay. So it should be about the same value. There should not be any difference at all because it's a simulated result anyway, right? So this is going to be then mu from, we can say, graph. 2 times pi times r times the slope of the graph, okay? All right, then the PE about the same, I think, will not change at all. Okay, any question? All right, then it's the same simulator, but we can reinvestigate the same information by keeping the current constant and then by changing the radial distance. Okay, that also let me change this part right here because there was a mistake there. That's why we had earlier issue. So it should be mu 0 I divided by 2 pi in this case. Mu 0 I divided by 2 pi. So this should be then slope multiplied by 2 pi divided by I. Okay. So let's take a look how the magnetic field changes as a function of radial. That should decrease rapidly because it inversely proportional 1 over r. That should decrease very rapidly as we increase the radial separation. Any question? Okay, then let's continue. Let's keep the current maximum value. That's okay. I think it's a simulated result, doesn't matter. But otherwise, the current value is actually too high. Okay. So I'm going to keep the maximum possible number because it will give us a larger value in Tesla, 20 amps. Okay. That really, really high number, but that's okay. 20.0 amps. I'm going to add 1 decimal place purposely. Radial separation unit meters, right? So unit meters, 1 over r. I need that because we would like to do a graph, 1 over r, right? That's going to be a linear graph. So that's going to be 1 over meters and the magnetic field in terms of unit Tesla. Okay, let's do one calculation and then we're not going to do the mu for each of the radial. Instead of we'll do the mu by using the graph directly, okay? So we'll start radial separation 5 and how far we can go. We can go to 50, which means we can go maybe each 5 at a time because I need about like 1, 2, 3, 4, 5, 6, about 8 data points, okay? So these two we can do maybe like at least 1 or 2 decimal places. And magnetic field we need in scientific notation, okay? Because that's very small number. 1 over r, you can do the calculation equal 1 divided by the cell value B52. We need that to make the graph, 1 over r. And the magnetic field directly from the simulator, 8 times 10 to the negative 7, okay? Equal 8 multiplied by 10 to the power minus 7. That will do the automatically scientific type notation. Now, what you have to do, you have to complete this table and then make these 2 graphs, okay, in your group. I think now you guys much familiar how to do the graphs, okay? So let me put you back into the breakout rooms then. Any question? Okay, then we'll start. Okay, so I did the graph magnetic field versus radial distance. That should be exponentially decaying graph, right? I fit that graph with the power law. Okay, if you do the trend line and then just click the trend line and then double click on the trend line, it appears as a linear line, and then double click and then change the option, trend line option right here into power law. Okay, so that will automatically fit it into the x to the power -1 because that's 1 over r. So the number in front of that we can use actually if we want to get the permeability from that too. And the graph number 2, magnetic field versus inverse radial distance, that should be linear. Okay, y equal mx type graph. And then by using those numbers in front of the x of both of them, I recalculated permeability. Okay, I think your graph has, your table number 5 has only one line. That's okay. You don't need to do the both. So in your case, you can use only the linear graph. That's totally fine. That's the slope of the graph, but I think I check with the both. So the graph number 1, if I use the R versus magnetic field, then you can see it has a little bit of error. 4.0083. If I use that number, then I'm getting little bit of error there. 0.2 is still very small, but for graph 2, I'm getting exactly 4.0 10 to the -6. So my percentage error went back to the same number we got earlier. Okay. All right. Any question? So complete the table 5 also. Anybody have any problem with the table 5? If you would like, you can add the both, okay? Add another line and then do the permeability by using both graph, but at least you have to have the one line permeability from the graph number 2, okay? You should have at least one permeability from graph number 2, okay? So this line you should have at least, but if you would like, then you can do the both. Okay, good. Any question? Okay, then let's take a quick break and then we'll talk about the solenoid. So that's something we actually skip. We did not get enough time Monday class. So we will go back and revisit the solenoid magnetic field by using the Ampere's law. And then that's actually theory part we needed for our lecture class anyway. And then we'll check out that by using the simulator, okay? This is the equation for graph 1 and then graph 2, okay, right here. And then percentage error equation. All right, so let's take a quick break. Question. Yeah. Figure number 4 trend line should be a curvature because you should fit that into power law, okay? So put the trend line first, then double click and then select the power right here on the trend line option. Then it should fit y equal a number times x to the power -1. Okay. All right, so let's take a look the solenoid. Doesn't matter, maybe maybe you should use about like 4 decimal places for particularly figure number 4, because then third and fourth decimal place you will see your numbers are changing beyond the 0, so that may be important. But for the figure number 5, 2 decimal places even enough because all the decimal places are 0. Okay. All right, so let's take a look at the solenoid then. Solenoid is just a wire but rotated into a look like a cylindrical shape. So that's a coil. So there's various type of coils, right? You can take the wire and then rotate again and again and again on top of each other. So that's also a coil. Okay, so this is the two endpoint of the wire. But the solenoid is not similar like that. So the solenoid is also a coil, but what it does, it actually has a wire but rotated into a cylindrical lengthier shape. Okay. So the one of the important concept, important assumption is that when we apply the Ampere's law for this one, we're going to assume solenoid is infinitely long. So technically nothing is infinitely long, right? So our assumption is that L is very, very, very large number. So the idea is that if you take the radius of this guy, so let's say diameter is D, because it's a, if you look at it from the side way, this look like a cylinder. So the radius, let's say diameter divided by 2, which is about R. And then the idea is that that R value is actually considerably less compared to the length. Okay, so that's the idea. So that assumption is important to produce the formula what we're looking into, but after we figure out the final equation, that equation is valid even R and L are not really super difference. Let's say L is about like 30 centimeters, R is like 5 centimeters, is still the formula is valid. Okay, so that's the idea. Okay, let's take a look what's the Ampere's law first. Ampere's law, let me write it down that on the last chapter note, because we can actually use that in our lecture note also. That will be useful. Let me write it down on the same papers. That should be easier. Okay, so this is actually the second law which we discussed on last chapter, Ampere's law. So what's the idea of Ampere's law? This is generally considered as a Gauss version of the magnetism. So if you remember the Gauss law, if you have a charge distribution, doesn't matter how many positives, how many negatives, and then so on. It can be any random charge distribution. What you need is to define the Gauss surface first, right? If you define the Gauss surface around this charge distribution, that dotted line is the Gauss surface, then the Gauss figure out a way to write it down, the total flux passing through the Gauss surface, that is equal Q inside the Gauss surface divided by the epsilon zero. So the similar law, which is actually figured out by Ampere for the magnetism, doesn't matter how the current line are actually aligned or how many current lines are there, but he figured out total magnetic flux passing through the current line. So the integral of B dot dl, okay, B dot dl, which is equal mu 0 times I enclosed, I inside. This is slightly different, okay, because in the Gauss version for the electricity, this guy pi is actually integral of E dot dA, right? E dot dA, closed loop. But for the Ampere's law, it is actually dl, okay, not dA. So it is not flux, it is actually total magnetic loop around the current distribution. So which means, let's say, for example, I have a current wire look like this, and the current is I. So if I want to apply the Ampere's law, what I should do, I should go r distance away from the current wire and then figure out magnetic loop. Okay, you already know how the magnetic loop look like around this current wire. So right here, magnetic field goes in, other side magnetic field is comes out. So if you look at the loop, it's going to be look like this. Okay, that's the magnetic field loop. So the magnetic field is around the wire rotating on XZ plane. Okay, this is X-axis, Z-axis, Y-axis. So this magnetic field loop is on XZ plane. So now if I want to apply the Ampere's law for this one, you remember we built this equation, what we needed earlier, we built that by using the Biot-Savart law, okay? Ampere's law actually extended version or simplified version of the Biot-Savart law. Biot-Savart law look like valid for only one source, but the Ampere's law can validate the magnetic field due to collection of sources, collection of magnetic sources, okay? Now, in this case, if I want to apply this one, the right-hand side, mu0 time I enclosed, going to be simple I only. But the left-hand side, I need to figure out what is the integral of B dot dl. So dl is actually a small part of this loop. In this case, loop is the magnetic loop itself, okay, field line. So the magnetic field around that loop is constant, so I can take it out. And then integral, closed loop, just dl. Let me write it down, this part also separately, B dot dl. So the magnetic field line's magnitude of the dl, cosine angle between the magnetic field line and the dl is actually 0 because dl goes around the loop, magnetic field is around the loop, magnetic field vector, cosine 0 is 1, okay? B dot dl, B takes out, integral of dl in this case is actually the circumference with radius r, that is 2 pi r. So which is equal mu0 I, then you can find the magnetic field from that equation very easily. Magnetic field due to current wire is mu0 I divided by 2 pi r. You can see the applying the Ampere's law is actually much easier than the Biot-Savart law. Okay, Biot-Savart has that cross product. You have to figure out that first and then so on. But the Ampere's law is very simplified version. Okay, any question? That's the second law you need for our previous chapter. Okay, chapter number 12. Now, the keep track on all of these laws because all of these basic laws, Gauss law, Ampere's law, all of those are actually at the end of the semester. We're going to be talking about the Maxwell's equation. When we're talking about Maxwell equation, those laws are converted into the Maxwell model. Okay, so the Maxwell did not technically figure out anything new. Before his time, all these great scientists figure out all of these individually for each cases. So he put it all of them together to figure out the simple mathematical model. So that's what we generally call the Maxwell equation. Okay, that's the starting point of electromagnetism. Technically, if you want to become a physics major, but any other field, I don't think advanced electromagnetism is required. Maybe doubly means the electrical engineering, probably they might ask you to take the advanced electromagnetism course, but otherwise that's not required for any other subject in the universe. Except the physics, you have to take 2 more electromagnetism classes. So those first class is starting from the Maxwell equation where we ending up, okay? So that's where the real electromagnetism. So what we're doing in this class is like very simple conceptual ideas, okay? All right, now what we like to see now in this case, not really just one wire, we would like to see actually collection of wires. Technically, I have a loop. So continuous loop look like this. Now this is our solenoid. Now, if you look at the solenoid, let's say current goes in from here, current goes out from the other side. If you look at individual loop, okay, so this particular endpoint look like the current goes in, and then right here look like the current goes out, okay. So the current goes in, current comes out, goes in, and then so on. Let's take a look the cross section of this solenoid. If you look at the cross section, it look like this now. Cross section mean you cut down from the XY plane, okay. This is X, this is Y, this is C, okay. You cut down on XY plane and then look at the cross section of the solenoid. Then it look like current goes in on the top. This is very lengthy coil, okay. Current comes out from the bottom. So that's a cross section now. If you look at the cross section look like collection of wires. So that's the idea. That's why the Ampere law is needed to understand that. So if I have a collection of wires, if I want to use the Ampere's law, step number 1, you need to have the Ampere loop, right? So that's the Ampere loop. Ampere loop should be a closed loop which magnetic field possibly goes around. That's what we're interested in, okay? You define the Ampere laws for Ampere loop for this one. Let's define right here. Let's start from there, and then maybe we can go down here, and then we can go down here, and then we can go back, and then we'll select the part of the wire collection, and then that's our Ampere loop. Okay, let's consider this is A, this is B, this is C, this is D. Then if I have the Ampere law, what you have to do, you have to apply the integral of B dot dl for this Ampere loop, which should be equal mu0 times I enclosed. Okay. Now this part you can do segmented. If you have integral, you can do segmented. I can do integral B dot dl from A to B, then the same integral from B to C, then the same integral from C to D, and the same integral from D to A, which would be equal total mu I enclosed. Now, which means I have to take a look how the magnetic field goes on each individual segment on my loop, okay? So let's take a look how the magnetic field look like. Now, if you have two wires here, let's pick one point to see how the magnetic field look like, this particular point. I have a wire coming out the plane. So if you put the thumb in upward direction, then all four fingers actually goes around it. So which means if I draw a line right here, magnetic field should be about 90-degree line. And then same I have right here from the other one. So the magnetic field should be 90-degree to that one, which means downward direction. If you take the force component, magnetic field component of that, there will be two component up and down, equal and opposite cancels out. Then you will be getting resultant component in leftward direction in the middle of the wire. So which means if I do the same thing along this line again and again and again, we will get the net magnetic field inside these loops exactly in the middle, much larger value. But any other component will cancel out. Resultant magnetic field going to be only on this word direction, okay? Inside our wire loop. Make sense? Following? And if you do the same to the outside, so what we're getting from the outside right here, so I have wire piece right here. So you have a magnetic field this word direction, from this one magnetic field this word direction. Again, if you take a look, Y component cancel out this word, you will get the resultant component this word. However, if you look at the component coming from this guys, that will be complete opposite. So I'm going to get resultant component opposite direction too. On the x-axis, total component outside almost close to 0. It may not be 0 exactly, but very, very small, okay? Extremely small. We can assume magnetic field outside of these coils are extremely small or close to 0. So when you measure that in a bit, you will see that, okay? Physically measuring it. Now, if you do the same assumption or the same investigation due to these two, inside what will happen, magnetic field goes in. So there's a magnetic field component this word direction due to reds, magnetic field component this word direction due to red positions. As a result of that, you will get another magnetic field due to red wires on the same direction. So the net magnetic field from the both corners of the wires inside the coil becomes much, much larger. So that's the idea of solenoid. If you have a solenoid, there's a strong magnetic field inside whenever the current in there, but the outside magnetic field almost 0. Let's say inside number is like 100 Gauss, then the outside number going to be like maybe 1 Gauss. So it's extremely small. We can assume outside is almost 0, okay? Relative to the inside number. That's the idea. Any question? Then if you look at the yeah, go ahead.
The 100 Gauss, that's outside the solenoid?
No, this is inside.
Inside. Oh,
This
okay.
is outside, okay? So solenoid inside is, if you look at it from the cross-section into the solenoid is a three-dimensional cylinder. So that's the inside, okay?
Right. Thank you.
And if you look at these corners, these two lines, let's take a look what will happen, because I have two wires now around it. So the one wire current comes in. Because of that, there are going to be magnetic field downward. The other wire right here, currents comes out. If you look at the fingers, then the fingers goes up here. So the magnetic field up and down due to two opposite direction totally cancels out. There's no magnetic field on BC and then DA. So which means now we'll apply the Ampere's law for this particular case. We know that should be integral total B dot dl, which is equal mu 0 times I in close. And then this part we extended, okay, integral B dot dl for A to B plus integral B dot dl from B to C plus integral C to D B dot dl plus integral D to A B dot dl, okay, which is equal total mu times mu 0 times the I enclosed. Now, if you look at it, this one, these components we don't need any longer. B to C, C to D, and then D to A. All of them becomes almost zero magnetic field. So we can cross out those things. So what we really interested is integral from A to B inside component B dot dl, okay, which is equal mu 0 I enclosed. Now this part again, B and DL in the same direction. You might get negative sign if the B and DL are opposite direction, but negative sign we don't care. In magnitude wise, we can just say B and integral DL. So the integral DL gonna be the length piece we selecting right here. Let's say this part, the length piece is L. So which means BL, which is equal mu 0 times I enclosed. BL, which is mu 0 times I enclosed. Now this I enclosed is actually a problem, because the reason, if you look at the I enclosed, I have many loops, right? So let's say this part is the length L we interested. So that part, I can't really say how much current is there, current wires is there. What we have to figure out is actually what we generally call the density of current wires. So which means, let's say I have total number of N loops on around this whole wire. So the N divided by L, we actually can say the number density or the loop density. Loop density means how many loop per each wire piece, okay? So which means if I have a total length L, so the L multiplied by small n gonna be the total number of current is actually associated with our length piece, okay? If I do that assumption, this In gonna be mu 0 times is small n times the I. Make sense? Good. That's the idea. Okay, sorry, total n times the I, total number of loops. Total number of loop times the I is actually the I enclosed or the I inside. So which means the magnetic field we can write mu 0 total n divided by L times the I total n over L, which is actually what we call the current loop density, okay? So that's the formula we actually needed for the magnetic field inside the solenoid, okay? Solenoid is just a coil. You cannot use the Biot-Savart law at all for this kind of scenario. That's not going to work, okay? Because it's a collection of loop. Biot-Savart laws can actually use only for this particular case. So that's the idea. That's why you can see in same concept. There's no different concept here. It's the same concept, magnetic field due to current wire, but I cannot rely on the basic idea. So I need the extended or simplified version. That's where the Ampere's law is very useful, okay? Because that can simply tell you what is the total magnetic field due to collection of the wires. However, when you're working on such a problem, you cannot still use it by just rely on the math itself. You have to build the problem conceptually, understand how to do this integral, you can't do the integral just like you do in the math problem. Just putting the numbers there or by relying on the math function, not going to work. So you have to break down the problem step by step, how this works, whether there's a magnetic field coming from the certain part or not. If that is the case, we may be able to get rid of those sections very easily and then end up with the simplified answer. Okay, that's what we done. Okay, this is the formula we interested for the solenoid. That's the idea. Okay. All right, so let's take a look what's beyond this one. We're just going to analyze this part by using the simulator, okay? Read the slide and then that has all the information. If you don't understand anything which we discussed earlier, part repeat look at the video, okay? Video recording has every single step, then you should be able to get that, okay? That for the question from Ahmed. Okay, so let's take a look now. One more quick thing. Now, the idea is that our assumption, this is actually look like infinitely long wire, but it's not really infinitely long. It is finite, okay? So the idea is current goes in, current goes out from here. This has totally n number of loops and then totally L length. So the ideally this L technically much more larger than the radius. So that's the idea because we interested magnetic field inside right here. That's where we interested, right? Magnetic field inside is much larger. Magnetic field outside is almost zero. But technically there's outside magnetic field, right? The reason why there must be outside magnetic field, if you look at it, this loop magnetic field always must create a loop. It cannot stay like that linear, okay? Magnetic field must always complete the loop, which means if I have a magnetic field line here, so that must complete a loop. So if I have a magnetic field line here, it must complete the loop. When it is complete in the loop, you should be able to identify magnetic field line poles. Poles mean whether it is a south pole or the north pole. Now to do that, you have to observe this loop from this angle. If you look at it from there, this is y-axis. Let's say the center line is x-axis. This is z-axis. Okay, I'm observing now on yz plane. YZ plane into the loop. So if you look at it there, current goes in here, current comes out from there. It's look like a current loop, right? This part. If you look at it, that part itself look like that. So it look like current come here, current goes there. Okay, it's rotating. So at this point, look like current goes in. At this point, current comes out. You look at it relative to the XY coordinate system, it's going to be look like this. Now we observing from here, okay? Now relative to that, which direction is the current rotating, you can actually identify what is that magnetic pole there. Because if you remember earlier, we done the magnetic field due to loop, right? Earlier case, I think one question number 5 or 6 on Monday. So if I have a magnetic field loop, if you put the thumb direction at any given piece of that wire, so let's consider only this particular part. If you put the thumb direction into that, and then you can take a look which direction the magnetic field line goes, whether the magnetic field line goes into that loop or coming out the loop. If you do this case, you can see magnetic field line look like going into the loop. Exactly at the center, it's going to be look like that. That's the magnetic field line direction. So inside this loop, because of that, magnetic field line directed from left to right, okay? Assuming magnetic field line go from north to south, then we can say all the magnetic field lines here directed thatward direction, come out thisward direction, complete the loop, and then goes out from thisward direction, complete the loop. So the both side of your solenoid has to have those field loops, okay? So but the magnitude of the field value is very, very less around here. Both of these sides are very small field value, but inside you're going to have a very, very strong magnetic field. That's the idea, okay? Any question? All right, now what we're trying to understand is actually this formula, okay? So the formula we built by using the Ampere's law for the solenoid, we'll take a look the validity of that one, okay? So now this is one question. This is, I think, one from the last in-class question set. You need to take a look that, okay? So you just need this equation to solve that question. Take a look. Some point I will upload the answer also for that one, okay? And let me give you quick another idea what we need for actually lecture class. Another idea is actually what we call the toroid, which is very similar concept, but there's a difference between the toroid and the solenoid, okay? Toroid is you take the solenoid like the slinky, for example. This is a solenoid, and then you take the solenoid, which is like a slinky, and then you rotate or combine the two endpoints of the slinky together. Then you will get the toroid. Toroid is actually a circle look like this, and then inside it has the loops. Now that's the solenoid inside, okay? Toroid is nothing new. It's actually a solenoid, but combine the two endpoints, these two endpoints, A and B, you connect together. Then you will get the toroid, okay? That's a toroid. This is actually a solenoid. So if you have a toroid, what's the difference in there? This is the difference. Now you can see magnetic field of the solenoid should be inside here. Outside is very small. So now for the toroid, magnetic field line is going to be look like that. It look like a circle. Okay, that's the only difference. So the magnetic field lines look like that. Inside you have a huge magnetic field look like a circle. So that how actually we can generate, for example, the particle accelerator. Because you have a huge magnetic field, if you make a huge toroid, then inside you can actually give a magnetic force where you want to accelerate the particle and then so on. There's a lot of various application, okay? One other thing now, when you want to develop the magnetic field equation for this one, that will not be the same as for the solenoid, okay? You have to take a look that carefully. Now our field lines are look like this. So each of your magnetic field lines is actually now a circle. So put a small dl for this one, then the magnetic field line is same direction. Then you should be able to do integral of b dot dl for this one very easily. B dot dl is equal same as mu 0 I enclosed. I enclosed is actually total current wire times the total number of loops. Let's say I have total number of loops n, and the current on each loop is I. So the I in gonna be then n times the I. And the B dot dl is the interesting part here. The reason B dot dl now not like the previous case. B dot dl, if I go exactly into the midpoint right here, let's say r distance away, B dot dl itself becomes B times dl 2 pi times r, right? So now you have to really do this integral part very carefully, okay? You should not end up with the same equation like you got earlier. Take a look at that one. If you get a time, I will come back to this point, okay? And let's first finish the lab. And then I think, yeah, we should be able to get at least 5 minutes at the end. I will come back and then take a look at the final equation for this one. Any question? Okay, let's continue on to that one. Let's first finish the lab and then I will come back to this guy, okay? So this simulator is actually different, but in the same website. You can see the link on page number 3, magnetic field on solenoid, and just click on that. We open the Excel page. Okay. All right, so we are on table number 6. Okay, we have a couple of tables there. We'll first try to finish that. Current direction now, in this case, we have to be careful because solenoid, I can't say current direction up or down, right? So it's completely different idea now. Let's take a look. This is our solenoid. Okay. Now you can see again, like for the same case earlier, current I can change from 1 to maybe 10 amps only this case. And the coil density, that is the small n, okay? Coil density means how many number of coil per unit length, okay? So the total coil divided by the length, that is a small n. And the magnetic field inside, that's the one we interested. You can see magnetic field inside is now fairly very large number. It's about 0.0025. It's in the order of 10 to the negative 3, very, very large compared to the previous case. Okay, that's the idea. If you have one single wire, it can produce a magnetic field, but very small. But if you rotate the wire or have the collection of wires, then you can increase the magnetic field by large amount. Okay, so that's why electromagnetism, all of those application, motors, turbines, any of those things are in a way depending on some sort of application with the coil, okay, transformers, all of those things in a way applied the some sort of cylindrical shape coils. Okay, now you can see there's outside field. Okay, you can see there's outside field and inside field because magnetic field should be a loop, but the question is that the outside field is actually very, very small, very weak, because inside magnetic field lines is actually getting very small, very closer to each other. And then the field density is much higher inside. Because of that, I have really huge magnetic field inside. But outside, magnetic field lines are actually separated by large distances. So each particular point, magnetic field strength is very small outside. So we're interested only inside magnetic field of the coil, okay? So that's the idea. So let's take a picture of this one too, because if you're planning on writing a report, you need that. Insert, illustration, screenshot, screen clipping. Let's take a screenshot, maybe around this part, should be good enough, I think. And that should be figure number 2, because these two figures should go to your procedure section, okay? Let's put that as a figure number 2. We can say magnetic field of a solenoid. Solenoid simulator should be figure number 2. And then let's take a look the very brief observation of how the magnetic field actually generate, and then what are the direction, things like that. So the current direction is relative to now your observation. Remember, you're supposed to observe through that angle, okay? You have to look at it inside of that cylinder. Then you can see current is actually going upward and then round look like that. Your right-hand side upward to the left-hand side. That is generally we call counterclockwise direction, okay? Current direction is counterclockwise, okay? Let's say counterclockwise. I'm just going to put CCW, counterclockwise. And if you look at it from sideways, thisward direction, current goes from your left-hand side to the right-hand side, okay? You can add that also by looking into the sideway, so the current go from left to right. Now, let's take a look how the magnetic field look like. Current is Amps, the coil density, technically equal large N over L. So the coil density should have to have a unit 1 over meters, right? So remember, like charge density concept, things like that. Here we interested the coil density, how many number of loops per unit length if you go this word direction, okay, from x-axis horizontally. And the magnetic field strength, Tesla, that as usual earlier. Those numbers not we interested, but we interested is the magnetic field in this table. Let's put the numbers anyway, 10 amps, and the coil density is 20 coils. Magnetic field is around 0.0025 2.5133 times 10 to the power minus 3. Fairly very large number compared to our previous values. And let's take a look how to identify the magnetic poles, right? Because now you know what this does. This coil becomes a magnet itself. That's the idea, okay? Because that's why the electromagnetism is actually always need the coil. Because what it does, you don't need the materials or anything to get the magnetic field. You just need the coil. You apply the current. As soon as you apply the current, what you have is the magnet. So now if I have a magnet and then we know the magnetic field line direction, by looking into the magnetic field line direction, I can identify what is the north pole, what is the south pole, okay? Usually how we define that, if you have a north pole and south pole, the field line should go from north to south always, assuming north pole is look like the positive charge particle relative to the electricity, okay? Which means if you release the north pole somewhere itself, then that should be automatically attracted to the south pole, okay? So in this case, you can see field lines come out from this side, magnetic field lines, your left-hand side, and then goes to the right-hand side, right? So which means my left-hand side should be look like the north pole. So the right-hand side should be look like the south pole, okay? That should be validated by current too. If you put the current upward direction, the thumb, by looking into this direction, that blue arrow, thumb direction, then you can see all the curly fingers are coming out inside this loop, okay? Put the thumb into the blue line and then rotate the curly fingers, then you can see fingers are coming out around this area. So the coming out mean this is actually acting like the North Pole right here, okay? That's the idea. So now all those red lines goes from starting here and then goes to the other side. So let's rotate, let's record that too here. Magnetic pole left side of the solenoid relative to your observation. Now it's depending on how you observe, okay? So you have to keep this way, and then relative to your observation, your left is acting like a North Pole now. And your right hand side acting like a South Pole now, okay? Now that should flip if I flip the current. That's why electromagnets are the most important gadgets in most of the application. Unlike you have a permanent magnet, it's difficult to manipulate accordingly what we needed. But if I have a electromagnet, it's very easy. I can flip the current, for example. As soon as I flip the current, you can see all the magnetic field lines changes. Now magnetic field lines coming out from your right hand side go to the left hand side. So the everything flip, right? So the everything is remaining same right here. There's no difference at all. These numbers we did not change at all. But your magnetic poles now is actually flipped. This side become a south, other side become a north. And if you look at it this direction, now you can see current is actually flipped relative to the circular. Then the current goes down from your right hand side, come to the left. So that is clockwise direction. Okay. Now you have a current clockwise. So that's the idea. Okay, now the rest of the tables, we just check in the numbers like we done earlier. But this part is so important, how to identify this pole direction of an electromagnet by looking into the current, because these are not visible. These red arrows are not visible. If you're doing this in-person setting, those red arrows are not there, right? You can't really see red arrows. What we can see is the deflection of the compass. That's all we can see. Okay. Yeah, there's no equation or anything. These just directly the numbers you're reading from the simulator. Yeah, these numbers right here. On your left-hand side corner, you have the current, 10 amps. You have the current, the coil density or the number density, which is about 20 per each unit length, and the magnetic field value. Okay, 0.025 in the green Tesla. So that's what we actually type here. Okay, I will add one decimal place purposely. Otherwise, it's look like very inaccurate numbers. So let's continue into table 6. Okay. Any question? Okay, so for this one, what we're interested is to check it out two things. First, we'll keep the coil density constant. Let's take a look how the magnetic field changes as a function of current. Okay. This should be table 7. Exactly correct. Yeah, please correct that actually. Last table should be table number 7. Okay. It should not be 6. Yeah, good point. Then let's keep the coil density 20. Okay, 20.0. Unit should be 1 over meters because it's large N over L, right? And then let's change the current as a function of we'll change the current and then we'll try to detect the magnetic field as a function of current. Okay. Current is unit amps, magnetic field unit Tesla as usual. And then let's take a look. Current will start from the minimum value, maybe like 1 amps. Okay. And then we'll slowly increase. Okay. 1, 2, and then so on. We'll increase all the way to 5, 6, 7, 8. Okay, 8 amps. We'll add 1 decimal place for that also. And then we'll see how the magnetic field changes inside. Okay. All right, so at 1 amps magnetic field is about 0.0025 equal sign 0.002513. Record all the decimal places. Okay. And also you can highlight this area, change this into scientific because still we have smaller numbers. So it's better to do the scientific, but I need at least 4 significant figures. Okay. Make sure you increase the number of significant figures to 4. Let's take a look how it changes. Let's increase the current into 2 amps. Now it's become equal sign 0.0002513, still about the same. How about current 3 amps? Wait, I think it did not update it automatically earlier. You may have to click outside and then click again. There are probably some issue, yeah. So you may have to click elsewhere and then click back on the place. Otherwise, it seems to be the simulator doesn't update automatically, okay? Or maybe instead of typing the number there, click and drag. I think that's better. Then it update automatically. Earlier 0.0002513 at 2 amps 0.0005027. That should be because it should increase. Okay, that makes sense. 5027. And then let's take a look the 3 amps. 307540 dot 307540 7540. Yep. Question?
For the
No, this one.
magnetic field
No,
for current
first one I should have one more zero.
Yeah,
there.
I was about to say that.
Yeah. So this should continuously increase. Okay. All right, then that's it actually. What you have to do, just increase current at a time 1 amps. Okay. I don't know whether we're going to have enough time to do another group work. We'll just finish this and then try to investigate last 5 minutes if I can take how the toroid formula look like. Okay, that's the important part for our lecture class. That might be useful actually. Let's finish this one first. Okay. All right, guys. So all you have to do, increase this slowly and then record the magnetic field. Then 2 zeros, 10053. Then at 5 amps, 2 zeros, 12566. Then 6 amps, 2 zeros, 15080. It should consistently increasing, okay. 7 amps, dot 00175993. Then 8 amps, 0020106. Okay. Now that's what we're expecting, because we know in terms of formula point of view, magnetic field should be just mu0 small n times I, or mu0 large N over L times I. So the small n is large N over L. Okay. So the B is directly proportional to the current. That's what we're expecting. So that's what we're observing. Okay. So let's take a look the same thing by keeping the current constant and then by changing the number density, because it's difficult to change if you have a set coil. It's almost impossible to do this change, okay? Because after you make the coil, there's no way you can increase or decrease that. However, we can do that by using a slinky. Everybody, I think, know the slinky. That's the coil which is very flexible, right? So if I have a slinky, metal slinky, actually we can do this experiment in our lab very easily, because we can set the slinky in a fixed length at the beginning, and then we can extend it manually. As you increase the length of the slinky, the amount of turns per given length is actually starting to change. So this is also possible to do in person class setting, okay? So the small n gonna be again large N over L. So the unit gonna be 1 over meters, and then the magnetic field is unit Tesla. So what we're interested to see how the magnetic field changes if I have the number density increases, okay? So let's keep the current at constant, maybe maximum number. And the number density will start from the low value. I can go from all the way to 20. Let's start at maybe like 2. Minimum we can go only 5. That's okay. We can start at 5, and then we'll increase maybe like 3 at a time. Okay, 3 or 4 at a time. So increase at 5 number density. And the magnetic field is about 0.306283. And also change this column number E into scientific notation with 4 significant figures, okay? And the coil density, I think we should keep it just a number there. Maybe 1 decimal place is fine, but it generally should be a round number, okay? Because you can have half a coil, but it's not really much meaningful. We're talking about the total turns now, okay? How many total turns per given length? So we interested full complete total turns, okay? So since I need about 8 data points, let's increase this by maybe 5 to 8. At a time, maybe 3 turns at a time, okay? So 8 turns per length. You can see the number increases from 3 zeros to 2 zeros now. 2 zeros, 1 0 0, 5 3. And then let's go 11. Yeah, that's okay, I think. We maybe don't need all the numbers. At least if we have like 5, 6 data points should be enough. You can go like 2 by 2. That should be fine too. So you can go like 5 to 7. Let's do that, 5 to 7. And then 3 zeros, 8796, 8796. Then let's go 9. turns per unit length, 2 zeros, 1131, 11310, and then 11 turns per unit length, about 2 zeros, 13823, 13823, and then let's do 13. Turns 2 zeros, 16336, and then let's do 15. 15, about 2 zeros, 1885. It consistently increasing, right? So that's the idea. So which means if I have a more denser coil, then we have actually a larger field. Okay, 17, it's going to be 2 zeros, 21363, 21363, and then let's do one more data point, 19. Then we will get 2 zeros, 23876. Okay. So that's the idea. That's why the electromagnet actually very useful now. If you look at it, these magnetic field values, these are fairly larger compare with the Earth magnetic field, okay? Because if you try to measure something, I need to have a larger number than the Earth magnetic field always. Otherwise, it is very difficult to detect because Earth magnetic field everywhere. And not only that, nowadays, if you try to do this kind of experiment, there are other issues. For example, if you have your computer or the laptop or mobile phone, those create magnetic field itself. Those magnetic field can interfere with our measurement because every time you have electronic gadget has various electronic instrument around there, various current passing through, you always gonna get a small magnetic field around it. That's why if you're doing this kind of experiment in person class setting, we have to clear the whole table and then put all your backpacks, all the computers, all the keys and everything. Anything can interfere with the magnetic field or can create the magnetic field, we have to put it away. Then only we can actually really detect magnetic field which we can produce with that particular item because the numbers are very small. Okay. Yeah, anything, depending on the type of alloy. Most of the alloys, the belt and things like that has aluminum-based alloy. Aluminum is a non-magnet, so generally not a problem. But if you have any metal can magnetize by using external magnetic field like steel or any iron particles in there, can actually interfere. Okay. All right, so let's take a look this same thing. That's technically about it. We completed everything what we need, but let's take a look in terms of graphical view too, okay? So we would like to see in terms of graph how the magnetic field behave. We know should linearly increase as a function of current. This also we know should linearly increase as a function of number density, okay? Let's take a look those two very quickly. Let's take two more graph, insert, charts, scatter plot. And let's add the data, select data. I would think everybody familiar with the Excel graphing now, okay? But if anybody need help, always ask, okay? Select data, add, X values should be my current in table number 7. And the Y values should be magnetic field. And click OK, that is linearly increasing. We could calculate in mu 0. Again, since we done that earlier more times, also we don't have enough time to do that. I think we have a few more minutes, but otherwise by taking the slope, we could do that calculation again, okay? Make sure you have axis title, trend line, linear, and also fit the trend line to the linear fitting. These three I can click because by using the slope, if I want, I can actually re-estimate mu 0, okay? But you don't need to do that since it is not asking here, but technically we could if we want to. Axis titles and the chart title, let's include that. Chart title, this should be magnetic field versus current. And the axis title right here, x-axis is the current, unit amps, and then the y-axis should be magnetic field, unit Tesla. Okay, guys, any question? Everybody okay with that? Technically, if I get this number right here in front of the y, because we know the formula is this, right? Mu 0 n times I. So I'm making the graph between the b and I. So if I get the slope of the graph should be mu 0 times the I. So I can re-estimate the mu 0, just divide the slope by the n, right? Mu 0 times the n. So we could do that, but it's okay. I forgot to add that extra data table there. That's okay, but you have the idea, okay? So let's take the same behavior with respect to number density, okay? What's the current we fixed there? Maximum number 10, that also you should record here on the table at the right-hand side of the table number 7, 10.0 amps, which is a very large number, almost very dangerous, such high current value. Let's make another graph, insert, chart, scatter plot, and then add data, and x values, in this case, number density, right? So that's a loop density, how many number of loops per length. And the y values again, magnetic field, okay? Field consistently increasing if I have more and more denser coil. Click OK, click OK again. Very nice linear graph, but the slope is different. That should be the case because earlier one x-axis is current, now the x-axis is number density, different numbers. I need the axis title again. I need the trend line format, and the format trend line. We need to click all of these three because we would like to see the equation. And also in the equation, make sure you format the trend line equation into categories scientific. Reason, if I want to re-estimate the mu, now what we're drawing is B versus N, right? So the same formula, B is equal mu 0 Ni, but now I'm making the graph N versus B versus N. So the slope of the graph now should be equal mu 0 times the I. So the mu 0 I can estimate again, slope of the graph divided by the current, okay? So that too you don't need to do, but make sure you understand that, okay? Sure. Table number 6. Okay. Anybody have any other question? Okay, then let's name this one too. Then we finish everything what we needed here. This is magnetic field versus loop density. Magnetic field versus loop density. This is the loop density, or the different terms people use. Sometimes it called number density, loop density, or turn density. Okay, so what we interested is how many loop in particular unit length. Okay, so that's why it should be usually a whole number. Okay, you can say coil density too, nothing wrong. Yeah, so different people use different terms. So we can say loop density or coil density, coil or loop density. And that is small n. Small n is large N over L, so the unit should be 1 over meters, okay? And the magnetic field on our y-axis is the same unit Tesla. Yep. And this calculation, I think we can escape. You don't need to include that one, okay? So since I forgot to include the data table for that one, that's okay. So just leave it from there. And let me take, we have like 2 minutes. So let me show you that calculation which we skipped earlier, which is part of our lecture class actually. Okay, so this guy, okay. So this guy, if I go back to here, and now what we're interested to see is actually this part, okay. What is the integral B dot dl? Now, if you take a look, magnetic field is around the loop is actually constant, right? Because if I have r distance away, if that is the loop, that's going to be r distance away everywhere around the loop. And then that magnetic field loop is actually a constant magnetic value, go around the toroid. So if I want to do that integral, I can take the B out, do the integral dl. So if you look at it, that equation, so we have integral B dot dl. So integral B magnitude, dl magnitude, cosine angle between them is 0, cosine 0 is 1. B is constant throughout the Ampere loop. I can take it out. Then I'm ending up integral dl. If you look at that Ampere loop, that orange line which I drew earlier inside the toroid, this is R. Now this is the Ampere loop what we interested, okay? Ampere loop. So which mean around that means it is a circumference, right? So the integral dl is actually 2 pi times the R, right? Circumference is 4 pi R, right? No, 2 pi R, that's correct. B times the 2 pi R, is that right? That formula? Let me check that quickly, yeah. So which means now if you go back to our initial Ampere loop equation, B dot dl is equal mu 0 times the I include. This part now we figure out magnetic field is strength times 2 pi R, which is equal mu 0 times the current is total number of turns times the current in one loop. So now the magnetic field is mu 0 Ni divided by 2 pi R. Now you can see this formula is not the same we got for the solenoid. Solenoid has a different equation, right? B0 is mu 0 is small n times I. So now you can see for the toroid, depending on where's the position on inside, depending on which position you're talking about the magnetic field, that actually has a different numbers, okay? Because magnetic field can varies from this point all the way to here, to the end point, because you have inner radius and outer radius, okay? Magnetic field changes from inner to outer. So if I go closer to the inner radius, then I have a stronger magnetic field. If I go outer radius, then I have the weaker magnetic field because R is actually changing there, okay? This R, that plays a role there. That not included in our solenoid equation, okay? So that's the idea. Any question? Okay, I think